minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Engines full power, and liftoff. Go Falcon, go IMAP, go Swimboat L1, and go Corruptors.
And we are flying 3 new missions on a 1,000,000-mile journey to track space weather. Good looking flight so far. Our tracking cameras getting a great shot.
That's right, so coming up is max Q, which is the maximum aerodynamic pressure, largest structural load the vehicle will experience. So slowing it down helps to reduce some of the load it experiences.
Falcon 9 is supersonic.
And that will help us recover and reuse the first stage.
Max Q.
Scientists have long been searching for answers in the sky to some of the biggest questions humans can ask, like how did the universe form? And more importantly, how did our own home in the solar system come to be such a perfect planet for life? When NASA's Voyager spacecraft launched in 1977, they gave us amazing insights into the planets of our solar system. But thanks to their enduring design, they also provided us with crucial information about the boundary of our solar system at the edge of our heliosphere. These data, sent back over millions of miles, led to more missions to further understand how space operates. Time and time again, with missions like NASA's IBEX and Parker Solar Probe, it became clear that our sun does more than just provide our planet with light. It actually protects the entire solar system. In 2018, NASA awarded a new mission to provide a detailed map of our heliosphere and gather data on the galactic matter that interacts with our solar winds. This mission is called IMAP, or Interstellar Mapping and Acceleration Probe.
IMAP positions us to answer some of the most fundamental questions in the universe about how particles are energized and how they define the environment in which our solar system was formed and evolved and formed life.
IMAP is a large spacecraft, it's about 10 foot in diameter, about 4 feet tall. It has 10 instruments, 3 of those have 2 heads, so 13 heads, making up 10 instruments. 5 of those instruments measure the local particles, the ions and electrons in magnetic field. Those are the ones involved in space weather. The other 5 measure the outer heliosphere and the solar wind sort of remotely. And so those 10 instruments make up our full payload.
The study of the plasma of the heliosphere started with early missions and included things like ACE and IBEX that's still operating. IMAP, because of the coordinated use of all 10 instruments, really does a unified job in a way that most spacecraft don't do. We're measuring magnetic field, light, dust, energetic neutral atoms, charged particles, and we're doing all of that, and that gives a better global view of what's happening with the heliosphere.
The heliosphere is the bubble that surrounds our solar system. It is made of plasma, the charged particles and magnetic fields from our sun. The outward flowing plasma is called the solar wind, and that blows against the material between surrounding stars, or the interstellar medium. The heliosphere shields our solar neighborhood from harmful radiation found in the interstellar medium as it moves through our area of the galaxy.
So we're collecting this data very, very slowly, atom by atom, and we're accumulating these full sky images of the emission region in the outer heliosphere.
So it would be almost as if currently we've got this really nice map of the globe, or the whole planet, but we don't actually know what the map of our city looks like.
We're now in the process of filling in all these gaps, seeing everything, getting a high-resolution map, maybe even seeing the dynamics of how the solar wind and dynamic outflows of the sun coronal mass ejections influence this region, and how that also interacts with the cosmic rays that come back.
IMAP is helping lay the groundwork for space weather prediction 20, 50 years from now. And as we get more reliant on technology in space and here on Earth, space weather is going to become more and more important.
We're not as isolated as we think. It's not just the risk of an asteroid or cometary impact. These radiation risks are real, and they are ever present. And we need to understand them, and we need to understand the protective systems we rely on, because we can take actions to protect ourselves more if necessary.
And I think it's really important to have the latest and greatest for forecasting space weather because of all the technology that we have right now, all the satellites we have in space. We rely heavily on GPS, and when there's a solar storm that happens, a really strong one that comes towards Earth, that can really impact communications and, satellite health, etc. So,
additionally, the ENA sensors are getting a better feel for the structure of our heliosphere and how that is used as a filter for galactic cosmic rays. And when we talk about manned missions either to the moon or to Mars, it's going to be very important for us to understand if we have a bunch of galactic cosmic rays coming through. That's where the radiation comes from.
It's going to be able to discover new things in new ways that no one ever anticipated. What are those discoveries going to be? It'll be fun.
It's an incredible human endeavor, what we're doing. The scientists and their teams of engineers that put the instruments together, right, which these things are measuring the invisible, right? And they're doing it in such a way that it's state-of-the-art precision.
I think there's some lesson from our solar system that we can learn and then probably extrapolate and hopefully allow us to understand the universe and humanity better. Yeah.
I think we're going to have a much fuller understanding of how our solar system interacts with the interstellar medium and therefore our place in the galaxy.
When you are looking to create 10 distinct instruments that can operate 1 million miles from Earth, you need to pull together a team with a broad set of skills. You need expertise in heliophysics, creativity, engineering, problem solving, mechanics, fabrication, data science, logistics, critical thinking, and communications. And they need to have experience designing and building for the challenging space environment. To find the people that match these areas of expertise, IMAP connected with 81 institutions and industry partners spread out across 34 states in the United States and brought together international collaborators in the United Kingdom, Poland, Switzerland, Germany, and Japan. All the different teams followed a schedule that provided 30 months to test and finish the instruments and then transport them to the clean room where the spacecraft was assembled. Thousands of people with unique skills building 10 instruments focused on one mission. It's this teamwork that allows us to accomplish something truly amazing.
You could have a whole team of astrophysicists, but you wouldn't build an instrument, you wouldn't build a spacecraft, you wouldn't be able to fly a mission. What you need is a lot of complementary skills and background and knowledge. You need some people who understand the science really well. You need people who can do the engineering. You need technicians who can do the assembly of the instruments and the testing. You frankly need people who can order the parts well and keep track of where they've all gone and that sort of thing. We needed some expert drivers to be able to drive around these very expensive instruments around the country and back and forth to Thermalvac in Alabama from APL and then down here to the Cape. So, we need people with a tremendously broad range of skills, and we've been able to put together a team of really great expert people across a lot of skills that have made this possible.
everybody has to know how to play their role and where they fit. And not everybody is going to be like the first violin by definition. Not everybody is going to be the tuba player in the back, you know, but they have to know exactly where they are and how they fit into everywhere else and be ready for their parts, but also fit in together like as a whole.
Great teams are networks of support. They support each other to get the job done, and they're always looking to try to support each other to better enhance the quality of that product.
It just improves efficiency, it improves the amount of ideas that you have. And when you get into a flow state, right, there's an individual like a musician or a writer getting in a flow state, but when you get into a flow state between humans where the ideas pass back and forth, really anything is possible, man. Because our imaginations, you know, the sky's the limit. They are unlimited.
The IMAP mission is a 10-instrument mission, and we have 10 instruments, 13 sensors, and we do both in situ measurements, which is measuring the local environment where the spacecraft is, and we do remote sensing of both energetic neutral atoms that are off of the boundary between the heliosphere and the local interstellar medium.
IMAP Ultra is one of the what we call energetic neutral atom cameras or imagers on IMAP. We have 3 of those: IMAP Low, IMAP High, and IMAP Ultra, and we named them like that based on the energies they cover. So from very low energy particles, very slow particles, all the way to very fast particles. Those energetic neutral atoms are actually the ones that allow us to see how the boundary, the interactions of our solar wind with interstellar space happen at the boundary of our solar system.
MAG stands for magnetometer, and it's an instrument that measures magnetic fields. The magnetic fields in space are really, really small. The magnetic field on the Earth, which we know the Earth has a magnetic field, you could measure it with a compass. That's really small. It doesn't really affect our lives day to day at all. The fields in space are 10,000 times smaller, and we're going to measure them to 1 part in 1,000. They're incredibly small to measure, but they're also enormously important because the magnetic field from the sun, when it arrives at the Earth, it interacts with our magnetic field on the Earth, and that's what drives a lot of these space weather effects that we're so worried about, the way that the sun's activity can damage satellites and harm astronauts.
SWE stands for solar wind electrons. We count electrons at different energies coming from different directions in space. SWE is part of the acceleration part of IMAP. We're not making the maps of things coming from the heliopause. We're looking at what the sun's doing and looking at space weather, which are the effects of that sun on the Earth and systems on the Earth.
What HIT is going to study, so we know about solar flares and coronal mass ejections, and these are these enormous explosions that occur on the sun. They're actually the largest explosions in our solar system. When they erupt, solar energetic particles, so these are subatomic, tiny charged particles, get accelerated up to high energies, often then pushed out into interplanetary space where we can then measure them with solar energetic particle instruments. And so that is what HIT is doing. It's the highest energy instrument on IMAP, studying solar energetic particles.
GLOWS is for Global Solar Wind Structure. For the IMAP mission, GLOWS is supposed to provide survival probabilities of energetic neutral atoms. But in the reality, it makes much more. It does much more. In fact, it investigates the latitudinal profile of the solar wind, speed, density, and of charge exchange rate of interstellar hydrogen.
IDEX is what we call an impact ionization time of flight mass spectrometer for dust particles. It is a very large instrument because the fluxes of interstellar dust particles flowing through the solar system is kind of low. So we need a large target area. And the way the instruments work, that the particles hit a highly polished gold target that will make them vaporize and turn into their constituent species, electrons and ions. And we use what we call a time of flight reflectron setup that I can tell you the composition, the type of ions that you measure.
they call this instrument, it's compact dual ion and composition experiment. It's an instrument that measures from the solar wind energies up into the energetic particle regime, and its scope is to characterize what particle comes off the sun and how they get accelerated into the regime that we see them being accelerated.
SWAPI is the instrument that I lead, solar, wind, and pickup ions. And that instrument measures the materials coming directly off the sun, that's the solar wind, and the plasma, and then there's the medium from interstellar space. There's neutral atoms that come in and they basically pick up charge in the solar wind because the UV radiation photoionizes these particles.
I personally think it's super cool that we're looking at things coming in from the heliosphere, we're looking at things coming in from the sun, and we're at one spot. So we're orbiting L1 in a rotating spacecraft, and we're looking at all the stuff going on around us. So it's not like just one focus. It's two focuses and how those two things interact together to get the science that the scientists want.
When a child is born, they don't know anything about nature. And they learn that from us adults. And they learn that from these pictures and these stories and books that they receive. And that story has evolved, all right? And IMAP is writing the next chapter in that story. We're gonna understand the solar system unlike we ever have before.
The standard constraints for any instrument are mass, volume, power, budget. Those are the standard constraints. IDEX was constrained on many of those. We were not on the list of instruments that were absolutely required to go to space, but we were very fortunate to be on this mission, and I believe we provided a really interesting new view of our heliosphere.
There were times when we weren't communicating, and then I think things were not getting done. Not because people didn't want to get it done, it's because they didn't realize something needed immediate attention, or they didn't recognize that this piece needs to connect to that. And it's no one's fault, but I think the communication is really important for that.
There's a preliminary design review and a critical design review. And what we did was we pulled in people from the other teams to serve as board members on those design reviews. So the payload office ran the design reviews, but we pulled in people from IMAP High to review IMAP Low. Again, they understand IMAP, they have a lot of technical expertise, they understand the requirements, they understand the science, and they can then review IMAP Low and give them ideas to make their design better and to better meet requirements.
We did see unexpected results in testing the instrument, really high counts when we shouldn't have seen them. And it really took the whole team working together. And it was actually months until we finally discovered the root cause. And once we had the root cause, we were able to fix this issue within 2 months. And we fixed it completely. We're not concerned about the issue recurring on orbit, which I'm relieved to say.
After vibration, we had a section of grid that was broken, basically during our final vibration testing. And we coordinated an effort with 4 of our engineers and then our entire science team to come up with a plan to replace it. What went into that was a lot of really careful planning meetings and a lot of give and take between the instrument team, the science side, and the engineering side. We had some pretty ideal assumptions going in on how it was going to go down, and the engineering team was able to sort of bring us back to reality, and we reached a really nice compromise between both teams.
It's a very complicated time. I find that I go to sleep pretty well, but I don't sleep that long before I'm waking up because my head's spinning with all the questions and issues and what if this happened or what would I do if that happened and that sort of thing. It's very exciting, very scary.
As each instrument was being completed, the spacecraft that would carry them was simultaneously being assembled. 10 feet in diameter and designed to always rotate at 4 revolutions per minute so that all the instruments would get a full 360 degrees of operational capacity. Everything was designed and custom built for maximum efficiency and durability.
We have techs, we have machinists, we have engineers,
all of whom have built up incredible skills. Some of the types of things that our machinists do is just amazingly complex, and they can do it very, very quickly and efficiently.
Working on the science side is one thing. Working on the instrument side and how it's built, how it's designed, and how it's tested, it needs a complete different set of skills, abilities, and it's another realm of knowledge that you need to know.
You know, anytime you're dealing with hardware and software and things coming together, a large part of our job is shaking out all the bugs and working everything out and kind of getting everything to work. So on launch day, when we launch that spacecraft and kind of hand it off to the mission operations team to operate it in flight, we want everything to be working together and smooth and all just like it's designed to do.
The countless hours that the engineers have spent assembling the instruments, putting the spacecraft together, the rocket engineers, all of these pieces need to work effectively, perfectly for this to then get into space and for us to be able to collect this data.
That human connection is what it's really about, because, I'm amazed at us as a species. Look around. The butterflies ain't making satellites. What we do is miraculous as a species of life on planet Earth. Wasn't very long ago, we were in the Stone Age. Wasn't very long ago, agriculture did not exist. And yet here we are today, taking it all for granted, right? Taking, smartphones for granted. It is miraculous.
That's 1 pound of prime USA beef.
In September of 2025, the team gathered in Cocoa Beach, Florida, to participate in the launch of IMAP that sat atop a SpaceX Falcon 9 rocket. It was a time to celebrate the hard work and, for many, a chance to meet in person for the very first time. Scientists and engineers from around the world brought their families and spoke to space enthusiasts at Kennedy Space Center.
We see a tremendous amount of variation over the course of a solar cycle. And so IBEX, we saw about 1.5 solar cycles worth of variation, and IMAP will seamlessly tie into that variation, and we can continue to observe how our sun and its variability affects the strength of the interstellar boundary.
Oh my God, I'm at the Kennedy Space Center, NASA Kennedy Space Center, and I go to meet people to talk about a mission I have worked on. Like the kid inside me, I was like, oh my God.
So that's gonna be color. What's this color? Blue. Okay. And then we're gonna put that right there.
I can't wait to have my kids over at Kennedy Space Center and then show them the morning of launch. I can't wait for them to see the rocket go off, and I think it's gonna be an experience that they're gonna remember forever.
All the subsystems on the spacecraft are verified, that they can communicate to the spacecraft via receiving data from the spacecraft. Commands are received on the spacecraft at the level of every single instrument and every system on the spacecraft itself.
I've spent this 10 years putting this mission together. We put it on a rocket, which is basically a big explosive thing, which is a controlled burn, and not all rockets work properly, and sometimes bad things happen. I'm looking for just a good launch, a nominal launch, and you get that. You wait an hour and a half in our case before we're in good communication, and we're let go by the rocket and all of that. And then hopefully what we see is that all of our subsystems are live and that they're working nominally and that the spacecraft's in good shape.
Please apply power to the H45 and H90 instruments.
Please apply power to the HIT instrument. Copy, applying power to HIT.
We are at launch being imminent, which is super exciting.
The flight director gives up go for launch at the 45-second mark. We have an engine ignition at 3 seconds before launch and a liftoff at 0.
Feeling the nerves right now. The fact that we have a 1 second launch window is hitting pretty hard in terms of just how everything needs to go just right at just the right time to press go on this rocket and get us out.
It's a big launch
on a historic launch pad at the Kennedy Space Center that has a history going back to the Apollo mission, and just to be a part of that history. Now I can see myself not only in the context of, the IMAP mission, but also just in the space exploration in general, is really kind of all building up inside of me into this ball of anticipation.
Little butterflies. Yeah. It's sort of like right before a big race. You're about to start something very exciting.
Just anticipating the launch is, it's thrilling because it's the accumulation of all the work that we've done and the work that the team has done, and not just for IMAP High, but also the mission and other instruments. So we're coming to a point where everything becomes real. We're going to start seeing data a week after launch, which is going to be really, really cool. And so what's exciting, I think, for me is, the launch is pretty spectacular, but it's the start of discovery.
Strong back retract has started.
This is NLM. NASA's go for launch.
Falcon 9 is in startup.
The launch director is go for launch. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Engines full power. And liftoff. Go Falcon, go IMAP, go Swivel L1, and go Corruptor.
I'm sure there is a momentary wash of relief that comes over for many people at launch, but for others, that's when the real excitement begins. A large chunk of the team, this is their goodbye to IMAP, and that will absolutely be emotional, but for others who have been on the team just as long, right, this is what they have been waiting for to start, and that's what these NASA missions come down to, is getting into space and getting that science returned back for the public.
And there it is, landed on the ship. Okay, I want to thank everyone for being us here today.
We're going to have to fly over to Boulder and get ready for turning on the instrument, looking at the data and making sure that everything's okay. But we're nervous, we're looking forward to it, but until we turn our instrument on, that's the moment when I'm going to relax. Until then, I'm not going to sleep very well.
IMAP deploy confirmed.
My father was always into Star Trek and Dune and all of those sci-fi things, and we would watch them together, and he shared that love with me, and I have really taken that and run with it.
So I'm dyslexic, so I didn't learn to read when I was young. And all the other smart kids were reading, and I wasn't reading, and so instead of reading, I was taking apart the radio and putting it back together and working on all kinds of stuff like that. And so I very early on became interested in mechanical and electrical things, STEM stuff. I'm quite good at math. I ended up in high school deciding that physics was really interesting because it seemed so obvious to me that, the world worked in ways that could be described by rules and laws that you could understand, and there was math too. And in the end, I think it was kind of an advantage.
My mom has a picture up of me in 3rd grade, I think, and we had to write this little poem, and it said something about how I want to explore Pluto and look at the stars, and then I ended up working on the New Horizons mission to Pluto. So that was a very full circle moment.
I wanted to be an astronaut, sure, but I think that was really just an easy tag to put on the thing that I really wanted to be, which was to be an explorer. And you don't have to go there these days to explore. You can build something to be that explorer.
In elementary school, I just started to saying I want to become a physicist, not that I was understanding what that is, but I think I had that idea that I will be in a lab doing experiments.
I will be the most nervous is when it comes time to turn on my instrument for the first time. So that will happen in a couple months from now. And getting it running for the first time and seeing that first measurement in space from that data that's the part where I think probably going to have a lot more nerves.
Lenny, I don't believe that analysis. Look at that first data point. It's up at 24.
Everyone is 30.
There are 3 or 4 fly specks above it and 20 fly specks below it. Commissioning is going great. We have most of the instruments on. We're starting to collect really cool science data, and we're getting close to the end of being up and running with our science mission.
Answers my really big question was, is our foil intact? Definitely is, and efficiencies are better than on the ground. It's been very exciting to just see how clean these counts are, to see how well it's behaved in space. Those detectors behaved really cleanly, and they started seeing counts around the same location where we saw it when we tested in the lab. So this instrument is doing really well.
SWAPI was turned on 2 days ago in high voltage mode for the first time, and we were thrilled with the results. They surpassed what we thought we would see. I think SWAPI and a lot of the instruments are very clean because of our excellent contamination control program. SWAPI immediately launched into its science mode and was producing an amazing profile of the solar wind. From the first 5 minutes we moved into that mode, or even the first 12 seconds. And so we were thrilled.
Things went so smoothly that we're just gonna leave the instrument here. Once we boost up those CEM voltages, we're gonna leave it here, and we're gonna give that time over to Glow's team, who are ready and excited to turn on their instrument. So thanks everybody.
Begin Glow safe procedure.
We go to flash our slot 3.
We get into our destination at L1 pretty soon. We'll go into orbit about L1. That's the point between the sun and the earth that gravitationally you're pulled on both directions at the same strength. It's a very cool place to be orbiting. We'll be measuring what's coming out from the sun. We'll be looking at the outer heliosphere, the edges of our solar system. We'll be putting all that great science together, and we'll be discovering things that we haven't even thought about yet because we've never had these sorts of really cool measurements all together in one place.
Glows, yeah, this is the known CMD DL data 32 failure after a flight software load, if I'm correct?
Yeah, this was expected for this packet, but only we doing our aliveness test.
So I expect this light curve to come up slowly and very noisy at the beginning. And then when we increase the voltage, it's gonna kind of smoothen and take the true shape.
Glows, we have successfully booted from slot 1. Standing by to continue to flash program slot 2.
That's great news, Park. Thank you.
I think it's always amazing to see how you can get groups of people to produce much more than what they would do as individuals, as a team.
I think everybody on the team is here and working together because we're all very passionate about what we're doing.
Teamwork is a loving family.
Collaboration.
Communications.
Creative.
Synergistic.
Trust.
Respect. Every engineer, every scientist has a different perspective and knows different things, and it's important to leave space for everyone to talk and for everyone to be listened to.
Teamwork is balanced.
Exciting.
Generous.
Bridge building. Everyone has their own thoughts about the way things should be. And so it's very important from my perspective that we make sure that everyone is heard and we get the best answer for IMAP as a mission, and we use that as the solution.
Grace.
Leadership.
Empowering, because what you get out when you're working with people is greater than the sum of the parts.
I think with a project at this scale, right, anything as big as IMAP, it's so important to trust the team dynamic.
Teamwork is having good leaders to recognize when things aren't going well, get people where they need to be in order to make progress, in order to help the whole team and lift them up and make progress on things.
Thrilling.
Passion.
Partnership.
A sense of humor. IMAP is a tremendous team. And truthfully, I said sense of humor for a reason, because when things get tough, it really does help.
I think it's the drive to succeed, the drive to make a difference in society, in humanity, is understanding big issues, what's out there, what's in our galactic environment.
I really am happiest when I've learned something new every day, And when I say something new, I don't mean something I didn't know in the morning. I mean something that nobody knew in the morning, something truly new, a new piece of knowledge for humanity. And many days of my life, I go into work, and by the time I come home, we've figured something out, and we've made some insight, or we've made some little breakthrough, and all of a sudden there's a piece that we understand that morning nobody in the world had ever understood before.
Pour all the knowledge, skill, and experience into a spacecraft like IMAP and launch it toward the sun, and you still only get half the picture. It's what we do with the data in the years to come that will reveal the potential of this mission. Making discoveries that go beyond our hypotheses and data models may be the legacy of IMAP, but a better understanding of our solar system and how truly unique we are in the universe, leading us to ask questions we haven't thought of yet. That is the legacy of the team assembled for this amazing mission.